What is up, Astro Geeks? It is your host, Aphelion, and welcome back to the Ephemeris podcast. It is officially the last episode of Season 1, and I've already talked about how proud I am of how far I've gone with the production of the podcast and how excited I am for the next season where we get into some different kinds of astronomy, but I'm going to save myself some breath in that regard, and we're just going to get into the topic of today's episode, the nebula, which I've prefaced multiple times, so no need to explain, why I decided to choose the topic. So we're just going to jump straight right in, real straightforward. So nebula as a whole, it's a very, very broad topic, and if I were to cover it, it would be a really, really long episode. So for the sake of the length of this episode, we'll cover some of the cooler types of nebula and leave out some of the more basic ones, which I will end up giving a little mention to. But the four cooler, quote-unquote, types in particular that we will be discussing today are H2 regions, dark nebula, integrated flux nebula, and protoplanetary nebula. So before we can get into all these cool nebula and what's going on with them, why they're not so basic, we gotta cover some base details about nebula themselves. So most people have a pretty good idea of what a nebula should be, but we're just going to be real clear with a specific definition here. They are regions with luminescent interstellar medium, and they tend to contain ionized hydrogen, cosmic dust, and such, so really cool elements that bring out a lot of nice colors, and that is part of what makes them really, really good photos, which we'll talk about in a moment. So they tend to be star-forming regions as well. For this reason, they have quite a lot of material that would make great stars, and the matter that's not used for stars in nebula tends to form planets. So there you go, you got some nice solar system forming material, if not just star forming material. And on another note, nebula tend to be quite huge. They can get up to like hundreds of light years in diameter, which is that is big. Like, if you've done image processing with some of the nebula, which I assume most people haven't, but at least you've seen a photo of it on social media through, like James Webb Space Telescope news. When you process those kind of images, they tend to be fractured, and the space telescopes that do capture it have to literally move their camera around a lot because of how big these things are once you zoom into the nebula. So yeah, as I mentioned, nebulas tend to be the part of astronomy that catches people's eyes because of recent findings with James Webb Space Telescope and the Ultra HD photos that come from that. Like Carina Nebula, Helix Nebula, Eagle Nebula, they're all very, very popular on social media because of how lovely the photos of them look. So yeah, that is pretty much nebula for you. And the two types of basic nebula, or what I would consider quite basic, are planetary nebula and supernova remnants. Planetary nebulas are just going to come about from the death of a sun-like star, and then supernova remnants, you can imagine, is just the remains of a supernova. So those things have pretty basic evolution, so not something I'm going to get into very deeply in this podcast, but there are four types of nebula that have some interesting things going on. So let's look at the first one, H2 regions. I mean, the name kind of gives it away. It's a region of interstellar ionized hydrogen, right? We talked about hydrogen being one of the elements, but this one's going to have a lot of it. Ionized hydrogen is going to be the main man in these nebula. They tend to have a irregular shape, and they contain quite a lot of stars in them. In fact, these stars that do tend to be in H2 regions are given birth to very quickly. And in terms of numbers, I think it's about 1,000, like thousands of stars in a couple of million years. And to put that into perspective, the sun is 4.5 billion years old. So that is many, many stars being formed at a fraction of the sun's age. So that's pretty wild. That's pretty bonkers. That is quite formidable for a nebula. These stars tend to be hot and blue, so what that'll do is that'll essentially ionize the gas around it and kind of fuel the fire of these H2 regions being very, very hot and forming these hot blue stars. As for their evolution, these sort of nebula don't necessarily come about on their own. They'll come from large molecular clouds. And usually with these kind of celestial objects, I'm like, okay, well, we should probably analyze what came before large molecular clouds to be able to understand more about H2 regions. But the thing is, with large molecular clouds, you kind of can't rewind the time. Large molecular clouds is where stellar evolution starts, right? So the only explanation that can be yielded is that, okay, large molecular clouds just kind of happen through gravitational collapse, and then there's a bunch of interstellar medium in a part of a space, or like a supernova shockwave will kind of bring interstellar medium together that's so hot that it creates ionized hydrogen regions. So yeah, when we look at nebula, it's hard to look at the evolution because of the fact that they come from large molecular clouds, which is literally the beginning. Afterwards, after H2 regions have exited their prime, they will become a star cluster because stellar winds will get rid of some of the hydrogens, leaving only the stars, right? So that's H2 regions. That's our first type. Then we have dark nebula. And I mean, if you think about it solely from the name, you might think, oh, well, you can't see them. Well, no, that's not quite how that works. Their name comes from the fact that it's so dense that it obscures objects behind it, like stars and other nebula, in the visual wavelengths. And it's known as absorption nebula for this reason, because it literally just absorbs the light, I guess, from behind it. And the story with dark nebula is that they tend to be part of greater molecular cloud complexes, so they're not necessarily on their own and just happen to be somewhere out in space. But let's investigate this obscuring visible light thing. How exactly does that happen? Well, that has something more to do with the the chemical composition of what's in the nebula that causes this opaqueness. So the two chemicals that are the culprits for this are frozen carbon monoxide and nitrogen. And what they do is they coat the particles in dense parts of the nebula. And yeah, they just cause it to be very, very difficult for light to penetrate through them. And just as a side note for my chemistry nerds, if y'all are in here, we've got some pretty cool chemical compounds that are happening in these nebula. Although they are transparent and don't have anything to do with them actually being dark nebula. So they've got carbon monoxide with the oxygen 18 isotope. I believe that's a fairly common one. Formaldehyde, cyclopropenylidene. Okay, that's a very, very difficult word to pronounce. I apologize for the absolute butchering of that pronunciation. Hopefully you guys are having a better time pronouncing that one. And then diazenylium, right? So I never heard of those chemicals before I researched this episode, so I just wanted to bring them up, even though I'm absolutely horrible at pronouncing them. But yeah, I found those to be cool. And yeah, that's dark nebula for you in terms of the chemical composition creating some kind of cool opaqueness. So that's two covered. Let's get into the third one. We've got integrated flux nebula, and this one's a bit puzzling. I will say so myself. There's little known about integrated flux nebula, but it's a very, very interesting idea. I mean, it exists, but the idea of their existence is very interesting. So they aren't integrated flux nebula are nebula that aren't illuminated by radiation from any stars within it, but are illuminated by our galaxy. And I can completely understand if that doesn't, like, that did not register at all. So let's try to draw some analogy here. So, like, imagine in the middle of the night, right? When it's pitch dark outside and probably pitch dark in your room, you turn on a flashlight in your room and you point the light outside the house through a dirty window, right? So the light is getting through from the medium that is your dirty window, right? An integrated flux nebula in this situation would be like the dirty window. Like, even though you're pointing light past it, it also kind of illuminates what's on the window, as well as, some other parts of the outside. But the main focus is that if you point a flashlight at that window, you're going to be able to see some of the dirt that's on that window. And that's what happens with integrated flux nebula, is that radiation that comes from other galaxies that are surrounding it will kind of illuminate it, right? So as for the rest of the cosmos, don't get it mistaken, they have their own light. We're not giving them light like a flashlight would, right? Just is out there. And to add a bit of terminology to the explanation, and be a little clearer, the light that our galaxy emits is integrating flux or luminosity into what appears to be a nebula. So integrated flux nebula, right? There you go. So flux in general tends to involve movement, but when we mean it astronomically, so that's going to be like bolometric flux. And if you don't know what bolometric flux is, just a measure of radiation using a bolometer. So anyways, that was a lot of terminology. Perhaps that's not the best explanation. Maybe the analogy works better for you. And yeah, that is integrated flux nebula. If you want to rewind, by the way, go ahead. I feel like if some of that stuff is not registering, definitely, I think if you give it another listen, you might get it. So lastly, we have Protoplanetary Nebula, and the name in this case is extremely, extremely confusing, and I'm going to address that first and foremost. This type of nebula does not have anything to do with protoplanetary disks or the protostar phase. It was a bit of an issue with the naming historically. When they named it the Protoplanetary Nebula, they wanted to indicate that it was before the planetary nebula, but now that we have like a protostar phase in there, it gets a bit jumbled up and mixed up. So essentially, the proto in the protoplanetary nebula just indicates pre. So it's more like pre-planetary nebula, right? And we know that planetary nebulas, again, are the more basic form of nebula that occurs when a sun-like star dies. So yeah, that is a lot of taxonomy. I genuinely apologize. Hopefully that hasn't sent you in a loop. But anyways, let's get into what protoplanetary nebula what they actually are. So they occur between a star's late AGB phase and their planetary nebula phase. And while I have mentioned the AGB phase before, I haven't really talked about what actually goes on in the AGB phase. So I'm going to give a long explanation with all of the details, and then if that's not clicking, the essential definition will be at the end of this spiel. So, long description. AGB stars, they have a hydrogen-burning shell, but when these stars get far into the stage, that shell becomes really, really small, and it makes the star really blue because, burning hydrogen makes a star quite blue. So this hydrogen burning causes the star to lose mass, and lost mass forms kind of a circumstellar envelope around the central star. So it's not being burned, it's kind of lost, but it's still surrounding the star, right? So protoplanetary nebula, they form when late into the AGB phase, the temperature of the outer layers of the star goes up, but the central star is too cold to ionize that circumstellar envelope caused by the hydrogen burning, and it can't really do anything with it. So what it'll do is the star will produce high velocity winds that kind of shape this circumstellar disk, and it makes it look like a nebula before the star inevitably dies and is left with an actual planetary nebula. So It's just a little bit of a phase in the evolution a of a planetary nebula. And what's also important and interesting is that these winds actually make the kind of circumstellar envelope, which is initially spherical, it makes it like look like a cylinder. So like axially symmetric would be the terminology for that. And what all of this means is that the disk around the star will always turn it into what looks like a bipolar flow of matter, kind of like a Herbig-Haro object, I guess you could imagine. But obviously, let's make it very clear that protoplanetary nebula doesn't have anything to do with protostars. So, yeah, those are protoplanetary nebula, and essentially what should be taken away from this description is that protoplanetary nebula happened before a star completely gets rid of its outer layers and becomes a white dwarf and a planetary nebula. It's just a bit of a transition. And that involves some morphing of outer layers while the star is still burning hydrogen and helium a little. So it's not quite done burning, so it'll kind of change the interstellar medium around the star, but it's not quite dead. And yeah, that is all I have for Nebula today, and that means that we have reached the conclusion of Season 1. Whew, that is a sigh of relief a little bit. Churning out podcast episodes is not easy, right? So you gotta really take a step back when you can. And yeah, thank you all so much for the support across all of the episodes. To be completely honest, I probably wouldn't have been as passionate about doing this podcast every single week if I hadn't seen an uptick in the statistics for my YouTube channel and Spotify. So I'm genuinely thankful for you guys' support. And for everyone who is viewing, I intend to keep this endeavor alive because I see you guys giving me the views, and I would genuinely like to keep this going. I'm continuing to learn a lot more about astronomy and podcasting myself through these episodes, so I also hope you guys are learning something too. And kind of major thing that has been floating around my head for a little bit that I do want to get off my chest is that if there are things that I covered or did not cover this season about celestial objects that you're wanting to know more about, I would encourage you to be your own astronomy enthusiast and seek out information regarding those topics, because for me, astronomy feels like one of those things where it's like, if you know, you know. Right? And as much as I would like to fulfill the know in of everyone, fulfill the know of everyone in terms of astronomy. Sorry, I'm tripping over my words a little bit here. Making a podcast around that it doesn't make the episodes fun or make them fun to hear. And a lot of the topics I went through and I decided not to make an episode about, I was like, not worth researching. They're a little bit too shallow, or there's too much info out there on that topic already, so I didn't kind of see a point in covering them, because obviously a little bit of my goal with this podcast is to make something that's entertaining. So a lot of the stuff that I did not cover, I would consider are things that you can kind of satisfy your knowledge in by doing a little web search. If you feel strongly that there are a couple of things that are worth covering, definitely leave me a comment. I would love to hear you guys' feedback so I can consider what to include in the podcast episodes going forward. And also, what you guys are interested in, because, YouTube has great ways of figuring out what people are searching for, but I don't think that's going to help me out a lot with, astronomy. Because, not that many people are, actively looking for YouTube videos that cover like really core parts of astronomy. So I will speak about season 2 when that comes around. I might decide to put in a week break so that I can add some more notes to the research I'm doing on some of the cosmology stuff, but I might not, because I do have a little bit ready to go for season 2. I will make that decision probably split second, last minute type of thing. But that's gonna come when it comes. And until then, farewell to season 1, obviously, and I will see you guys in the next season. Peace.